Okay, so let us begin. In this video, we will be discussing kinetics and kinematics and how we can solve any force-related problem using these two. So the first thing we will discuss is kinetics. Now, kinetics we know is basically means motion, and for the purpose of this video, kinetics will basically be referring to that branch which deals with accelerations of bodies. So to, our first step in our procedure to solve a force-related problem is to draw a kinetic diagram. And this means that we have to draw all the accelerations of all the bodies given to us in a certain problem or question. So a kinetic diagram may look something like this, where A is the common acceleration for the block and the bob, AC is the centripetal acceleration of the bob due to circular motion, and AT is the tangential acceleration of the bob, again in circular motion. Now the next step in our procedure will be to analyze the body kinematically. Now what kinematics means is the study of forces. And to draw a kinematic diagram, we have to draw a diagram of all the bodies involved with all the forces acting on the bodies. Essentially, it is just a free body diagram. So this will be the next step in our procedure. So a kinematic diagram of the problem we saw before may look something like this, where we have a normal reaction force, we have a weight of the block, we have the weight of the bob, and we have tension force in the string. Now once we have our kinetic and kinematic diagrams, what do we do next? Well, we then equate them, and we equate them using Newton's second law of motion. You know that is the mathematical formula for Newton's second law. F is equal to ma. So what you'll see that the F actually represents the kinematic side. The kinematic diagram will give us the left hand side, and the kinetic diagram will give us part of the right hand side. So it will give us A. So what we do is we multiply every acceleration in the kinetic diagram by the respective masses to get the entire right hand side. Then we simply equate the two, kinetics and kinematics, and separate them into equations and solve them. So here you have a summary of the entire process to make it easier to understand. Just go through it once. So we first set up a coordinate axis system. We then analyze the problem kinetically, then analyze it kinematically. We then multiply every acceleration on the kinetic diagram by the required mass. And then we equate the kinetic diagram to the kinematic diagram by Newton's second law. This is actually the most important step in the procedure. We then get equations in the x and y direction respectively and solve them to finally get our answers. Okay, now let's look at a simple example. So we're going to solve a force problem using kinetics and kinematics. So consider a block of mass m placed on a table, and we want to find the acceleration of this block in this direction, given that no other force acts on this block. No, we're not pushing it or pulling it in any way. So our first step is to set up a coordinate axis system. Remember the process? So we have j direction upwards and positive I directions to the right. Now the next step in our process is to analyze our question or our problem kinetically, which means to draw a diagram showing all the accelerations of all the bodies. So let's do that. So we have our block, and it is accelerating with an unknown magnitude of acceleration in this direction. So we'll just call that acceleration A because we don't know what it is. Leave it as a variable. Now the next step is to analyze our question kinematically, or to analyze all the forces acting on the bodies. So let's do that. So what are the forces acting on this block now? Well, there'll be a weight force, mg, and there will be a normal reaction force exerted on the block by the table here. So now we have a kinetic diagram and a kinematic diagram. And our third step, or our fourth step rather, if we include the coordinate axis, is to multiply the accelerations in the kinetic diagram by the respective masses. To equate, this will help to equate the two. Now we just put an equal sign. And you notice that this acceleration here which we got, remember F is equal to ma is Newton's law. The F comes from the kinematic diagram, and the kinetic diagram gives us half of the right hand side, or A. So we multiply by M to get the complete right hand side and enable us to equate the two. So now let's just equate the two. Let's write the equations out. Before we do that, however, one important point to note is that we need to keep in mind the coordinate axis system. We need to write the forces in accordance with the system. And you'll understand why in just a minute. It makes it easier to solve. So we have MA in the I direction, N in the J direction, and MG in the minus J direction. So let us just write the equation out now. So MA in the I direction, that's from our kinetic diagram, is equal to N in the J direction minus mg in the j direction. Notice I've just taken the minus out from the j and put it in front of the entire force. You can easily do that. So now this ma here, or this is from the kinetic diagram, and this mj minus mg is from the kinematic diagram. Now to solve this equation, what we can do is solve in I and j directions separately. And that will actually allow us to get a lot of information about this problem. So what it means is that we separate the I terms and we separate the j terms. So the only I term is the ma. On the right hand side we have no I term. So ma is equal to 0 is one equation. Similarly for the j term, no j term on the left hand side. So we get n minus mg on the right hand side. And from these two equations we'll actually get a lot of information. So we get a is equal to 0 and we get n is equal to mg. And this is actually stuff we already know from common sense. If there's no external force, we know that the acceleration will be 0. Similarly, we know that the weight is always equal to the normal reaction force exerted on the block. But we've now done it kinematically and kinetically. So now we'll look at a slightly more complex problem. So we consider an inclined plane at an angle theta with the ground and a block of mass m kept on the inclined plane. And we want to analyze this block. We want to get all the equations we can for this block. And if it was a problem, you would need to solve for something. But once you can write the equations out, solving should not really be a big deal. It's just a matter of a simple bit of algebraic manipulation. So we'll just discuss how to solve the kinetics and kinematic equations and how to get them across. So the first step is to set up a coordinate axis system again. And this time I'll set up my coordinate axis system differently to the way I normally do. I'll take I to be the direction parallel to the inclined plane and J to be the direction perpendicular to the inclined plane. You can also take the regular coordinate axis system the way we normally do. It doesn't really make a difference. I just find this one easier, and you'll see why in a minute. So our first step in our process is to draw or analyze this body kinetically. So we draw a diagram with all the accelerations. So there we have the inclined plane, angle theta, and the block of mass m, and we just write an acceleration of say a, and we assume it's downwards. If it's upwards, it doesn't really matter, it will just become negative at the end. So we just assume it's downwards, and we actually know it will be downwards. Next step is to analyze this body kinematically. So we draw all the forces acting on this body. So we have a normal reaction force and a weight force. Now what we do is we actually resolve this weight force into components which are in keeping with our coordinate axis system. So we take mg sine theta and mg cos theta parallel and perpendicular to the inclined plane. And this is actually why I selected my coordinate axis system like this. If I had taken the normal coordinate axis system, then we would have to resolve both the acceleration and the normal reaction force. Like this, we only have to resolve one force, which is the weight. But you can also do it that way. It's just a little more work. And now the next step is to multiply the accelerations in the kinetic diagram by m, and then equate the two using Newton's law, second law. Now before we write it mathematically or write the mathematical expression for this, we need to remember to maintain the directions. So we have our MA in the kinetic diagram in the minus I direction, We have our n in the positive j direction. We have mg sine theta again in the minus I direction, and we have mg cos theta in the minus j direction. And now we can write out our expression, our entire equation. So from the kinetic side, we get minus ma in the I direction. Note, I've just taken the negative sign from the minus I in front of the entire expression or the entire term. So we get minus ma in the I direction is equal to, and now we come to the kinematic side, minus mg sine theta in the I direction. Again, I've done the same thing, taken the negative sign outside, plus n in the j direction, minus mg cos theta in the j direction. And this expression is actually what we need to get. Once you get till here, you can solve for anything that anyone can ask you. You can solve for mass, you can solve for acceleration, you can solve for the angle. So getting till this point is the tricky part. Solving it is not very difficult. Let's just solve it though. So we need to separate it into the I and j directions. So we write all our I terms first. So we have minus ma and minus mg sine theta. Those are the only terms in the I direction. And when we simplify, we'll see the minus sign will cancel and the m will cancel. And we get that a is equal to g sine theta. Similarly, if we equate in the j direction, we get 0 is equal to n minus mg cos theta. These are all the terms in the j direction. And if we just rearrange that, you'll get n is equal to mg cos theta. Now you see, by solving these questions, or by solving these equations rather, we have got information that we already know. We know the acceleration down an inclined plane is g sine theta, where theta is the angle of the inclined plane. And we know that the normal reaction force is always mg cos theta. But now we have got it using a simple process and using kinetics and kinematics. And this process can actually be applied to much more complex problems as well.